Hey everyone, and welcome to This Explainer. I am absolutely thrilled to have you here today. So, we are jumping right into what I like to call the ultimate chemical kitchen. We're going to uncover the exact math, the sheer logic behind how matter interacts to literally shape our entire world. I mean, from the food we eat to the air we breathe, it all comes back to these fundamental rules of chemistry. But before we really get cooking here, I want you to think about something. How in the world do you count something you can't even see? Seriously, think about it. How do chemists precisely measure and mix these completely invisible atoms to create, everything from life-saving medicines to explosive rocket fuel? It feels like magic, right? But as you'll see, it's just pure, brilliant math. Okay, let's dive into this. Here is our roadmap for today's explainer. First, the building blocks of matter. Second, the mole concept explained. Third, stoichiometry and chemical recipes. Fourth, finding the limiting reagent. And finally, number 5, solutions and their concentrations. All right, part 1, the building blocks of matter. So every great recipe starts with ingredients, right? Well, in our chemical kitchen, that base ingredient is just matter. And just like you'd organize a pantry into spices, flours, and liquids, chemists classify matter to keep everything straight. It's broadly split into pure substances and mixtures. Pure substances can be single elements, like a solid block of iron, or compounds, like pure water. Mixtures, on the other hand, well, they can be homogeneous, like a perfectly stirred glass of sugar water where it all looks uniform, or heterogeneous, like a bowl of cereal where you can clearly see all the different pieces. Now, here is the absolute golden rule of this kitchen, handed down by Antoine Lavoisier way back in 1789. The law of conservation of mass. Basically, it means you can't magically create or destroy these ingredients. Whatever mass you start with for your reactants, you absolutely have to end up with in your products. It's kind of like the universe's ultimate accounting system. Moving right along to section 2, the mole concept explained. Okay, so if mass is always conserved, how on earth do we connect the physical mass we can actually weigh on a scale to those invisible atoms we're reacting? We need a secret code. And that code is the mole. Now, don't think of the little furry animal digging up your yard. Think of it more like a chemist's dozen. If you go buy eggs and ask for a dozen, everyone automatically knows you mean 12. Well, when a chemist wants to count atoms, they ask for a mole. It's just a standard counting unit that takes these impossible numbers and makes them totally manageable. But unlike a dozen, a mole is mind-bogglingly huge. I mean, we are talking about Avogadro's number, 6.022 times 10 to the 23rd power. That is a 6 followed by 23 zeros. It's massive. Yet the real beauty here is the precision. 1 mole of carbon-12 atoms weighs exactly 12 grams. It perfectly scales that invisible, microscopic world, right up to the macroscopic world we can actually see and touch. And this brilliantly illustrates the true power of the mole concept. It acts as a bridge. It completely converts atomic mass units, which really only apply to a single microscopic atom, directly into molar mass, which means physical grams you can actually scoop out and weigh on a lab scale. It literally bridges the invisible to the visible. Which brings us to section 3, stoichiometry and chemical recipes. So now that we know how to actually count our ingredients, let's talk about mixing them. Stoichiometry. I know, it sounds like an incredibly intimidating word, but I promise it's really just the process of reading a chemical equation like a precise baking recipe. As John Dalton pointed out in his atomic theory back in 1808, you can't just toss ingredients together randomly and expect to get a cake. Compounds form when atoms combine in very predictable, fixed whole number ratios. You need exact proportions. And that is stoichiometry in a nutshell. We use those big numbers in front of the molecules in a balanced equation. We call those stoichiometric coefficients to predict exactly how many moles of product we're going to get. You can kind of think of those coefficients as the recipe's serving size. It tells us the exact, non-negotiable ratio of moles we need for our reaction to work perfectly without wasting a single atom. Let's head into section 4, finding the limiting reagent. All right, so what happens in the real world when our measurements aren't totally perfect? This is where the math really hits reality. Let me ask you this. Have you ever tried to, say, double a batch of chocolate chip cookies, but halfway through you realize you just ran out of flour? Well, it doesn't matter if you still have a massive mountain of sugar and chocolate chips sitting there, you can't make any more cookies. That flour, That's your limiting reagent. It gets completely consumed and dictates exactly how much product you can actually make. The leftover sugar and chocolate chips are your excess reagents, just sitting there after the reaction forcefully stops. So the absolutely crucial point here is knowing how to find that limiting reagent before you even start mixing things in the lab. And here's a super simple, foolproof 3-step method to do just that. Step 1, balance your equation. Step 2, convert your initial starting ingredients into moles, and then divide those initial moles by their stoichiometric coefficient from the balanced equation. Finally, step 3, just compare those numbers. The smallest ratio is your limiting reagent. It's basically the bottleneck for your entire reaction. Let's actually see how this plays out with a real-world calculation. Imagine we're reacting some iron and sulfur together to make iron sulfide. We weigh out our ingredients on the scale, and we find we've got 46 grams of iron and 32 grams of sulfur. Now, using that handy mold bridge we talked about earlier, we convert those physical grams directly into moles. That math gives us 0.82 moles of iron and 0.72 moles of sulfur. Now we apply our steps. The balanced equation for iron sulfide requires a perfect 1-to-1 ratio, 1 mole of iron for every 1 mole of sulfur. But look at what we actually have in our beaker. We have 0.82 moles of iron, but only 0.72 moles of sulfur. Since the recipe calls for equal parts, and we only have 0.72 moles of sulfur, well, the sulfur is going to run out first. Our sulfur is the limiting free agent. Once that 0.72 moles of sulfur is entirely used up, the reaction hits a brick wall and stops entirely, leaving us with a little pile of leftover unreacted iron. Here's another really quick example for you. Say we mix 4.0 grams of sodium hydroxide with 6.5 grams of hydrochloric acid to make table salt, NaCl. If we convert that to moles, it's roughly 0.1 moles of NaOH and 0.178 moles of HCl. Once again, this is a 1-to-1 recipe, so clearly those 0.1 moles of NaOH will run out first. It limits the entire reaction, meaning our final theoretical yield of table salt is capped at exactly 5.844 grams. No way around it. And finally, Section 5, Solutions and their concentrations. So far, we've mostly talked about solid grams and moles, but what happens when we take these ingredients and dissolve them into a liquid solution? How do we go about measuring them then? Well, this addresses a massive pain point for chemistry students literally everywhere: molarity versus molality. I know, they sound identical, but they actually measure totally different things. Molarity, with an R, measures the moles of your solute divided by the total liters of the mixed solution. Molality, with an L, measures the moles of solute divided by the total kilograms of just the pure solvent. So it's total liquid volume versus pure solvent mass. Now, why does this distinction actually matter in the real world? Well, imagine you're a chemist working in a lab where the temperature swings pretty dramatically from the morning to the afternoon. If you're using volume-based molarity, as that liquid heats up, the volume actually expands. Your total liters go up, which means your calculated molarity goes down, even though you didn't physically take any ingredients out of the beaker. But mass never changes with temperature. So if you use mass-based molality, your concentration stays rock solid no matter how hot or cold the lab gets. It is such a brilliant, crucial distinction to make. Let's just quickly walk through a calculation to see molarity in practice. Say you have 25 grams of ammonium chloride, and you dissolve it to make exactly 500 milliliters, so half a liter of solution. First up, we use our mole bridge to find that 25 grams equals 0.467 moles. Then you just divide those 0.467 moles by 0.5 liters, and boom, there you have it, a perfectly calculated concentration of 0.935 molarity. And honestly, that brings us right back full circle. I want to leave you with kind of a wild thought about Antoine Lavoisier's rule that we discussed earlier. If the law of conservation of mass dictates that atoms are never, ever destroyed, well, where are the atoms of your ancestors right now? Think about it. They're in the soil, they're in the trees, in the oceans, and maybe even in the air you're breathing right this very second. Matter is just continually recycled, over and over again, through these endless chemical recipes. It's a completely mind-bending reality, all governed by the incredible fundamentals of chemistry. Thank you so much for joining me on this explainer today, and hey, keep exploring.